back to the series on real analysis. Today we're going to be investigating the set of real numbers from the perspectives of completeness and separability. So since we're going to be working with the set of real numbers, everything that is associated to a totally ordered set applies, including the Weyl ordering principle and also Zorn's lemma. So let's introduce a couple concepts that you probably already know, especially if you know those two theorems that we've discussed before. So the first concept is an upper bound. So we're going to say that U is an upper bound as long as that element is larger than or equal to all elements in that particular set S. Keep in mind, just because U is an upper bound does not imply that that element is an element of that particular set S. You can practically take any graph from pre-calculus that has a horizontal asymptote above it and it's always increasing like an exponential function. Any element that is above that horizontal asymptote would be an upper bound for that relation, but that point does not belong to that relation, right? But it's still an upper bound. Also, same thing applies for lower bounds. We said that L is a lower bound as long as it's less than or equal to all elements in that particular set S. And again, if L is a lower bound, that does not necessarily imply that that person or that element or that object L belongs to that set S, and you can easily use exponential functions again as a counterexample for that. Just as a definition, if it is both bounded above and bounded below, then we say that that set is bounded. And if it's not bounded, that means we call it unbounded. So when we say unbounded, that means either A, it's not bounded above, B, it's not bounded below, or C, it's not bounded above nor below, right? It's just practically, like the tangent function, for example, right? So upper bound, lower bound, bounded above, bounded below, and unbounded, right? So let's introduce another block of definitions before we start getting into our theorems. Now let us assume that S is a subset of the set of real numbers, and let's assume that it's firstly bounded above. Then U, let's assume that U is an upper bound of S, is said to be a least upper bound, sometimes called the supremum of S, if it satisfies two criteria. The first is that it must be an upper bound of the set, and that upper bound must be less than or equal to all other upper bounds for that set, i.e. U is less than or equal to V for all upper bounds V of S. Also, similarly, if S is a subset of the set of real numbers and it's also bounded below, with L a lower bound of S, then we say that L is a greatest lower bound, or infimum of S, if it satisfies, again, two characteristics. The first being L must be, of course, a lower bound of S, and it must be greater than or equal to all other lower bounds of S, i.e. M is less than or equal to L for all lower bounds M of S. Right? Now, in terms of notation, there are a couple different notations that some people will use. So for the supremum of S, some people will use SUP of S, and some people, so that's focusing on the word supremum, and some people will use the acronym for least upper bound, so LUB of S. So if you see either one of these notations, SUP or LUB of S, and you're working with a totally ordered set, then you can view those as synonymous to one another. And the same thing goes for infimum, that's abbreviated by INF of S, and some people also use GLB for greatest lower bound of S. So those are just some common notations that are used for these concepts. So let's just talk through a couple little, corollaries or lemmas that you get from these little definitions, just to see that you're ready to be equipped with counterexamples. So if the supremum exists, that means it has a least upper bound. So since it has a least upper bound, that means it has an upper bound, which means that it's bounded above, right? But just because it's bounded above does not necessarily imply that a maximum exists, right? So just because it's bounded above does not imply a maximum exists, because keep in mind, a supremum and an upper bound need not belong to that set, and maximums have to belong to that set for it to be called a maximum, right? And also, if we have, for example, if it's bounded above, does that imply that a supremum exists, right? So let's sort of think through that for a moment. Well, if we sort of think about that for a moment, let's just draw some nice pretty function, let's just draw this function, which is definitely, let's say bounded above, right? So this is a upper bound for this particular relation. And let's sort of draw this particular line. That's an upper bound for that relation. That is not an upper bound for a relation because there's some points in our set that are above that. But obviously purple and green are line values that represent upper bounds, and maybe that also is an upper bound. So does there exist a least upper bound for this sequence? Right? So does supremum exist? At least for a set of real numbers, provided that it's bounded above. We'll explore this little case in just a moment. So, also let's consider another case. The answer is yes, by the way. Suppose that we have that a maximum exists. Does this imply that a supremum exists? All right, a least upper bound. So think about that for a moment. So the very important question is, well, what exactly do you mean by a maximum? So usually if you want to sort of create a nice definition for maximum, I would probably go with a global maximum, right? So if a global maximum exists, this is usually equal to the supremum of the set. Now, if people want to be a little bit more technical with this and say, okay, suppose that we have a local maximum that exists. Does this imply that a supremum exists? No, right? So this does not necessarily imply that a supremum exists, right? And you can practically take any function like a cubic, where, for example, that would be your local maximum because it's, greater than or equal to all values locally in that particular set S or in the neighborhood of that domain value, but it sort of goes up to infinity. So the supremum and also a global maximum does not exist as well. Okay? So those are just some of the things that you can sort of think about at this sort of present time with the things that we have. So let's ask a question, and this question is actually pretty interesting. Can a set, if it does have a supremum, so can a set have more than one supremum? So what do you think? Can a set, if it does have a supremum, have more than one, like 2 or 3 or infinitely many? The answer is, take a guess, no. Right? And this is a very important property because practically what we're saying is that if the supremum does exist, it's unique. So let's go ahead and see if we can prove this nice theorem. And if you want to pause this video and try and prove it on your own, feel free to do so. So let's formally state our theorem that we're trying to prove. So suppose that S is not the empty set, and let's assume also that S is a subset of the real numbers, and let's assume that U is a supremum of the set S. Obviously, it doesn't need to belong to S. It can be, above S, whatever that means. And then this supremum is unique. Right? So supremums, if they exist, are unique. Right? So let's see if we can go ahead and do this by contradiction. Or let's suppose that, it does have 2 supremums. So suppose that both U1 and U2 are supremums of S. Right? So since they're both supremums of S, that means that U1 and U2 are upper bounds of S. Right? Because if they're least upper bounds, that means they're also upper bounds. It's a less requirement of values, but they are indeed upper bounds. Right? So when we say that U1 is an upper bound, what are we saying? That means U1 is greater than or equal to X for all X in S. So that's what we say when U1 is an upper bound for S. And we also have that U2 is greater than or equal to X for all X in S, because U2 is an upper bound as well. Right? And again, notice that U1 and U2, again, do not need to belong to S. Okay? So since U1 is a supremum of S, then that means U1 is the least upper bound for S. So if that is the case, that means u1 must be less than or equal to u2 because it is the least upper bound, right? Because u2 is an upper bound, and since u1 is a supremum of s, then that means u1 is the least upper bound. Agree? Let's also create a parallel argument for u2 because we know that since u2 is a supremum of s, then u2 is also the least upper bound of s, which means that u2 must be less than or equal to u1. And why is that? Well, we know that u2 is a supremum of s. That means u2 is the least upper bound of s. And we know that u1 is an upper bound for s as well, right? And keep in mind, we're working in the set of real numbers, so we can do our typical combinations of inequalities and equations. So from this equation, what do we have? So we have, if we focus on, in particular, u2, then we have that u1 is less than or equal to u2. That's from the first inequality. And we also have that u2 is less than or equal to u1. That comes from the second inequality, right? So if we take this inequality and subtract u1 from both sides, so subtract u1, subtract u1, subtract u1 from all sides, what we have is 0 is less than or equal to u2 minus u1 is less than or equal to 0. And what number is in between 0 and 0? Well, that obviously implies that u2 minus u1 is identically equal to 0. And that implies that u2 and u1 are identically equal to each other, which means that the supremum, if it does exist, is unique, right? And a similar thing can be said about infimums, right? So let's just state this. So similarly, if the infimum of s exists, it is also unique, right? And I invite you to try and prove that on your own. The next theorem that we're going to be looking at is a very, very important theorem that we're going to be using a lot later on when we start talking about sequences and convergence in terms of limits for sequences. So it says this: suppose that U is an upper bound for a non-empty set S, where S is a subset of the real numbers. Then U is the supremum, the least upper bound of S, if and only if, so this goes both ways, for every epsilon greater than 0, there exists an x that depends on epsilon. In particular, this x belongs to S, such that the distance between that element in S and the least upper bound of S is arbitrarily close to each other, or the distance between them is arbitrarily small, right? Because if U is not the supremum, and x epsilon would be greater than or equal to all other values, then in some sense x epsilon would be the next supremum that would come into play here, right? So let's see if we can go and prove this particular and very fascinating theorem. And of course, since this is an if and only if theorem, we have to go both ways to prove this, right? So let's go this way. So let's suppose that U is the supremum of S. And let's assume that epsilon is an arbitrarily small but positive number. If that is the case, that means U minus epsilon, by the properties of the real numbers, is less than U, right? So if that is the case, since U is the least upper bound, that means that U minus epsilon is not an upper bound for this particular set S, right? So since this is true, that means there exists some x that depends on epsilon that belongs to S, with U minus epsilon being less than x epsilon. So let's sort of think about why that is the case, right? So let's sort of draw our picture. So there's our least upper bound U, and there's our U minus epsilon located there. Because since we're in a subset of the real numbers, if U minus epsilon does not belong to the set S, and U minus epsilon is still greater than or equal to all those values, that means U minus epsilon would be an upper bound. But since u minus epsilon is not an upper bound for that particular set S, that means there's some value that is larger than this particular element S, right? So let's assume that that point is located there. And this is our x subscript epsilon. You can say, okay, well, how would I define such a x subscript epsilon? Well, you can say, okay, it's the average of u and u minus epsilon. Obviously, x would depend on that epsilon. That's why we're subscripting that x with such things, right? So that practically proves the existence of such an object. Now let's see if we can go in the opposite direction. So what we're going to do is we're going to be letting u be an upper bound of the set S. And again, it's not necessarily in the set S, right? But if it is in the set S, then it would be by default the least upper bound, right? So if u is an upper bound, that means that u is greater than or equal to y for all y and s. And let's assume without loss of generality that y and u are not the same element, right? So our goal is to answer the question, is y an upper bound of S? And if so, is it possibly the supremum of S? Right? So let's see if we can answer these questions. So what we're going to do is we're going to define epsilon to be the difference between u and y. Because we know u is greater than or equal to y, that means u minus y must be greater than or equal to 0. So we're going to define epsilon to be that distance, and this is obviously greater than or equal to 0. Right? So if we're assuming that y and u are not equal to each other, if we sort of implore this little assumption, then that means we're going to have that epsilon, which is going to be u minus y, is strictly greater than 0, assuming that u is strictly greater than y. Right? So if that is the case, then we have that obviously epsilon is greater than 0. So what we have built up to this point is, let's sort of draw a picture. Here's my y, here's my u, and keep in mind the only reason I can draw these little diagrams is because R is a totally ordered set, right? So y is less than or equal to u, and all the other points between these 2 points are going to be ordered as such, right? So as usual, this is going to be my distance, epsilon, and therefore there exists some real number between y and u such that this is going to be x subscript epsilon, right? So if that is the case, that means there must exist some x in S such that y is equal to u minus epsilon, right? And that's obviously less than x subscript epsilon, and that obviously is less than u. Agreed? Keep in mind, what is u minus epsilon? U minus epsilon is just a fancy way of saying y in this particular picture, and that's what creates that sequence of inequality. So if that is the case, since u is an upper bound and y is strictly less than that, that means it's not the least upper bound. So that means y is not equal to an upper bound of S, right? And since that is the case, and since we have that epsilon is arbitrarily small, that gives us that u is the supremum of this particular set S. Now let us introduce the superstar of today, and that is the completeness axiom. We're calling it the completeness axiom because we're going to be taking this as an axiomatic foundational statement, and we're not going to be proving it. All right, so it practically joins the reins with the axiom of choice, right? So the completeness axiom and the axiom of choice are going to be building practically all we need here. And the completeness axiom says this: every non-empty set of R that has an upper bound also has a supremum. So this goes back to our quick little conversation at the beginning of this discussion was, if it does have an upper bound, does it have a supremum? And I was like, yeah, that's true, but in some sense it's true because we take it as truth, right? But the completeness axiom doesn't just say it has a supremum, but it has a supremum that is also a real number. And this is very, very beautiful, at least in my eyes, right? So regardless of the set of real numbers you have, if it's bounded above, it's always going to have a supremum that's always a real number. That's really cool, right? So before we get into some of the little results and examples of this, let me just quickly define a couple things that are going to be very useful, at least on the convenience side. So let's assume that S is again a subset of the real numbers, and we're going to let R union the numbers plus infinity and minus infinity. We're going to denote this as R star. So this is again the extended set of real numbers. Right? So definition 1. So if S is not bounded above, right? So not bounded above, does it have a supremum? Well, we're going to define the supremum of this set S to be equal to positive infinity. And if S is not bounded below, then we're going to define the infimum of the set to be equal to minus infinity. That says infimum. And lastly, if S is the empty set, then we're going to define the supremum of the set S to be equal to minus infinity. And you might want to think sort of why we would want that to be the case. Right? So if we take these things as definition, you can see the convenience that this actually brings, because what do we have as a corollary? We have that every set that's a subset of the real numbers, including the empty set, has an infimum and a supremum that belongs to the extended set of real numbers, right? So every subset of the real numbers has an infimum and a supremum. And that is very convenient to have. Right? So let's look at a couple numerical examples just to make sure we're comfortable with this idea of infimum, supremum, bounded above, bounded below, and all those things. Right? So example. So let's assume we have the set S, which is defined to be equal to 1 over n, where n belongs to a set of natural numbers. So what does this look like? So we have 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. So what type of set is this? Well, this is obviously a countably infinite set. So countably infinite set. And how could you prove that this is a countably infinite set? Well, obviously we can take, f of x to be equal to 1 over x, where the domain of this is equal to the set of natural numbers. That gives us the outputs, and let's assume that the codomain of this set, which is also equal to the range of this particular relation, is going to be equal to the number 1, or the set of 1's only, Cartesian product with the set of natural numbers. That will give it to you. Right? At least in terms of isomorphisms, what we have in that particular thing, because we always have 1 on top and the natural numbers on bottom, right? So we have, I guess, another way we could write this. I'm going to cheat with notation here. Let's do 1 divided by n. Right? That's a fun little set notation. It is valid in some sense, but in some sense it is sort of hand-wavy. But hopefully you know what I mean. Right? So if this is the case, then what do we have? So is this a bounded above set? So a couple of things that are very useful to know. So if x belongs to the set of positive natural numbers, which is bigger, 1 over x or 1 over x plus 1? You should be able to show that 1 over x is greater than 1 over x plus 1. The proof is actually very, very trivial if you just cross multiply or whatever we mean by that. Right? So if that is the case, that means 1 is bigger than 1/2, and 1/2 is bigger than 1/3, and 1/4 is bigger than 1/5, and so on. So that means 1 is greater than or equal to y for all y in this particular set S. So that means that 1 is an upper bound of S. Agreed? So if 1 is an upper bound of S, does that imply that it is the least upper bound of S? Not directly, or at least, right? So what we need to do is we need to say, okay, for any epsilon greater than 0, our goal is to show that 1 minus epsilon is not an upper bound, right? So if we get arbitrarily close to epsilon from the left and show that that is not an upper bound, then we have evidence to believe that 1 is indeed the least upper bound, provided that it is an upper bound in the first place, right? So this is that little theorem that we proved about the set of real numbers and upper bounds and least upper bounds, right? So if this is the case, then what do we have? So we know that 1 minus epsilon is going to be less than 1, right? Because epsilon is a positive number, so 1 minus epsilon is like, 0.00009 or 0.9999999 or something like that, right? So if that is the case, then we know that 1 minus epsilon is not an upper bound for S. So it's not an upper bound for S. And why is that the case? Well, 1 belongs to that particular set S. And if 1 minus epsilon is an upper bound for that set, then, this 1 minus epsilon has to be greater than or equal to 1, which it's not, right? So keep in mind, when that upper bound belongs to the set S, it's usually very, very easy to show that that maximal element is indeed the least upper bound of that set, right? So we've shown that 1 minus epsilon is not an upper bound for the set S, so that means 1 is equal to the supremum of S, right? And again, also note that the maximum of the set S is also equal to 1, right? So one could, in some sense, say that if you have a maximum and it exists, and obviously it is unique, then that indeed is the supremum of that set, right? Another little exercise that I just want to leave for you is to show that the infimum of this set, 1 over n, where n is a set of, in the set of positive natural numbers, this is equal to 0. But it's very easy and important to show that the minimum does not exist, right? So the minimum doesn't exist, but the infimum does exist, right? So that's very, very important, and I definitely recommend you try and prove that on your own. The next theorem that I want to take a look at is called the Archimedean property, and it says the following. Suppose you choose a real number x, any real number at all. Then there is always going to exist a natural number n that depends on x, such that that natural number is always going to be bigger than the real number that you have chosen. Right? So that's the Archimedean property. Another way that you could say this theorem or rephrase it is that the natural numbers is not bounded above, more so not bounded in the set of real numbers. Right? You could also say, regardless of the natural number that you chose, there is always going to exist a real number that's bigger than the natural number you chosen. That's also equivalent as well, right? So let's see if we can go ahead and prove that the natural numbers is not bounded above, at least in the set of real numbers. So let's assume that n is less than or equal to x in the set of real numbers, and let's assume that this is true for any natural number m. That is, we're going to be assuming that n is bounded above by x. Now again, x need not be an element of the natural numbers. X could be natural. Well, that wouldn't make sense, would it? But if x were a natural number, then bounded above still could be the case. In that case, it would probably be the supremum of the natural numbers if that were the case, right? So if this is true, what do we exactly mean by n is less than or equal to x? Well, that would mean that x is an upper bound. Upper bound for a set of natural numbers. So what do we know about the set of natural numbers? So we know that the natural numbers is not empty, because we know at least 1 is a natural number. And we also know that n is a subset of the real numbers. So n is a non-empty subset of the set of real numbers. That means that n has a supremum in R, right? So that's the completeness axiom of the set of real numbers. So another way of saying that is that there exists a number, in particular there exists a unique number, because we know supremums are unique, such that u is the supremum of the set of natural numbers. Right? So keep in mind, if it's a supremum, it's an upper bound, and it's the least of those upper bounds. Right? So if u is the least upper bound of m, then that means u minus 1 is not an upper bound of the set of natural numbers. And that's extremely obvious in the case that u is a natural number. Now, I just want to sort of take a moment and pause this proof and sort of think about what we mean by this, because keep in mind we're assuming that n is bounded, right? So we're assuming that n is bounded. So if we're assuming that n is bounded, that means the supremum is finite also. Right? We're assuming that the supremum is less than positive infinity, right? Because remember that little definition that I included earlier on, that if it's not bounded, i.e. unbounded, then the supremum is defined to be infinity. But we're assuming it's to be bounded, which means that u, the supremum, is finite, right? And you could approach this proof in a different way and use the fact that n is an infinite set, right? Because if n is an infinite set, then you know, well, who indeed is this character u, right? So, but we don't want to use the properties of the Archimedean principle because we're trying to prove that to sort of lead to contradiction, right? So we're just going to continue in this direction here. So we have that u minus 1 is not an upper bound of n. So if u minus 1 is not an upper bound of n, that means there's an element in the set of natural numbers that is sort of bigger than or equal to, in some sense, this u minus 1. So that means there exists, let's call this new number v in the set of natural numbers, such that u minus 1 is less than v, right? Because if it's not an upper bound, that means there's something bigger than it in this set. So if u minus 1 is less than v, that means u must be less than v plus 1. And keep in mind, if v is an element of the set of natural numbers, that means v plus 1 is also an element of the natural numbers due to the closure property of the set of natural numbers, right? But keep in mind, we assume that u is the least upper bound for n, right? U is the supremum of n. And v plus 1 is an element of the natural numbers, but it's bigger than that least upper bound, which contradicts the fact that it's an upper bound, more of the least upper bound, and that's obviously our contradiction, right? So that means that n is not bounded above, which means you'll always be able to find a real number bigger than or equal to whatever natural number you have chosen, and vice versa. You can always find a natural number bigger than or equal to whatever real number that you have chosen. Now, there is another way of rephrasing this theorem, and I'll just treat this as a different theorem because it does have a couple different implications. If x is a positive real number, then there exists an n that again depends on the set of that x that you have chosen, such that 0 is less than 1 over nx less than x. So here we're sort of diving into the set of rational numbers. So regardless of the real number you have chosen, there always exists a natural number whose reciprocal is between 0 and that real number you have chosen, right? And this proof I will leave for you. It's actually not too bad. So let's just do a little quick exercise because this is actually pretty interesting. So let's do a couple. So let's recall e, which remember is the sum from k is equal to 0 to infinity of 1 divided by k factorial. So that's e to the power of 1 generated from this power series, which keep in mind is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial and so on. And all of these terms are obviously positive. So this is going to be equal to 1 plus 1 plus 1 half plus 1 sixth plus 1 over 24 and so on. Right? So that's obviously going to be equal to, let's do 1 plus 1 plus 1 half. We know that's equal to 2.5. And then we have the 3 factorial onwards term. So I'm just going to write that as the sum from k is equal to 3 to infinity of 1 over k factorial. And we obviously know that that is a positive number. So if that is the case, that means we have 0 is less than 2.5 is less than e, right? Because if we subtract that term off, we have a number that's slightly less than e, because you remember e is like 2.7, 1828, 1828. So we have that 2.5 is a lower bound for e. So we have that, right? Also, since it's at least 2.5, that means if we consider, for example, the first term, we also have that e is bigger than 1, right? So e is bigger than 1. So 0 less than 1 over 1 less than e, right? So that's another little lower bound that we could get, right? So if we want to sort of, use that little theorem that we stated, obviously that is a natural number, right? So there's our x that we've chosen. There always exists a natural number that's, sort of its reciprocal is between 0 and that number e, right? And you're like, well, it's kind of lame. Well, are there any others that you could choose? Well, you could choose 2, but keep in mind, if we choose 2, we're actually getting farther and farther, right? Because 1/2 is less than 1 over 1, right? But that is another natural number, and it could even go farther. For example, 1 over 50. That's obviously less than or equal to e, but it's even worse of a lower bound, right? So in some sense, the most ideal natural number in this particular case would be 1. So it's the greatest natural number such that the real number you have chosen, its reciprocal falls in between that real number and 0. Right? So there's definitely a lot of approximation theories that can sort of build upon this, which we'll definitely revisit at a later time. Just as another example for a number that you probably already know, the square root of 2 over 2. So we know that 0 is less than the square root of 2 over 2 because it's a positive number, and that's also less than 1. And if in case you don't know that that's less than 1, keep in mind that 0 squared is less than 2 over 4, and that's less than 1 squared. Because keep in mind that's the same as, that thing squared. Agree? So since that is the case, and you're like, okay, well, can I get an approximation for the square root of 2 that's better than 0, 1? Obviously, 1 is a nice upper bound, but 0, maybe we can do better than that, right? So we know that 0 squared is less than 1 over 9, and that's less than 2 over 4. We know that that's less than 1. Right? And we know that by the increasing property of the square roots, we can take the square root and the inequality still remains preserved. Right? So you're like, okay, well, where did I get this 9 from? I chose that to be a perfect square because I need to build the square root of 2 out of this. Agreed? So in this particular case, I have 0 is less than 1 over 3 is less than the square root of 2 over 2 is less than 1. And I have this lower bound and upper bound for the square root of 2 over 2. So there's our little natural number, nx. And here's a question. Is there better for this, right? So obviously you only have a couple other natural numbers to go. You have n is equal to 2 and n is equal to 1, right? N is equal to 2 and n is equal to 1. So you would have to figure out, okay, well, would 2 work for this? Is square root of 2 between 0.5 and 1? I'll leave that little explanation for you, and it's obviously true that square root of 2 is not between 1 and 1, so 1 is definitely out, right? But this gives you some realm for approximating. Agreed? So let's see if we can get another theorem out of this sequence, and I think this theorem is actually pretty nice. So theorem 5. If x is a positive number, then there exists an n in the set of natural numbers such that x is always strictly between nx and its preceding natural number. And in case that nx is 1, nx minus 1 would be 0. Right? So you can always find two natural numbers that approximate whatever number that you have. Right? For example, if I have e, can you give me two consecutive natural numbers that this is between? You should be able to verify quite easily that e is always between 2 and 3. And what about, for example, 5/4? Can you find two consecutive natural numbers that make this true? Then you should be able to show that 1 is less than 5/4 is less than 2. Regardless of the real number that you have chosen, you should always be able to approximate it within one natural number according to this theorem. And the proof, again, I leave for you because it practically follows as a corollary from the other theorems we've discussed. So up to this point, we've discussed several different things and theorems and concepts and examples and applications associated to upper bounds, lower bounds, supremums, infimums, and what we call the completeness axiom for the set of real numbers, which led us to the Archimedean principle and a couple other results that are very useful for approximations and representations of real numbers. Now let us close this discussion off with two new concepts. So, we say that a subset of a set X is dense in that larger set X if either A, every point of that bigger set belongs to that set S, i.e. they're equal, or every point of X is arbitrarily close to an element of X. Right? So dense in X. Practically, if you look at any number in X, if you sort of create a little epsilon neighborhood around that point, you're always going to have an element of S in that set or that neighborhood. And if a metric space X is separable, then what we mean when we say it's separable means it contains a countable dense subset. So, before we get into the last theorem of today, I just want to recall a very important result that we proved last time. In particular, if we take our delta, this is indeed a metric space if we take the absolute value of x minus y to be our metric. So it satisfies those four properties of a metric. And the second property that we proved at another time was that Q is countable. Q is countable. Right? So Q is countable. So we have a countable set, and we have a metric space R delta. So the theorem that I want to close out with today is the following. So let's call this theorem 6. Q is dense in R. And if Q is dense in R, since Q is countable, that would imply that R is separable. So R is a separable space where Q is a countable dense subset of R. Right? So another way that we could say this is if X and Y are elements of the real numbers, and let's assume without loss of generality that X is less than Y, then there exists a Q in the rational numbers such that Q is always between X and Y. So that's what we mean by dense. You choose any two unequal real numbers, there's always going to exist at least one rational number between them. Always. And that's very interesting. So let's see if we can prove it. So proof. Let's assume that X is larger than 0. Obviously, this theorem says between any two real numbers, so it also includes negative numbers, but if you want to prove it for the negative case, it's practically the same exact proof. So if X is bigger than 0 with Y bigger than X, then we have that Y minus X is going to be a positive number. All right, so we have a positive real number. So if we have a positive real number, then by one of those theorems I mentioned earlier, that means there exists a natural number, n, let's call it, such that 0 is less than 1 over n is less than that real number. Right? Keep in mind that's just a real number. So if that's true, then that means 1 over n, if we just focus on the left two statements, is going to be less than y minus x. That means that 1 must be less than by cross multiplication. N is a natural number, so that's going to be less than ny minus nx. And that's going to be giving us nx plus 1 is less than ny. All right, so that's one thing that we have from that statement. Agree? Keep in mind, if x is a positive real number and n is a positive natural number, then that means that nx is also a positive real number. Right? So that's a real number too. So if that is a real number, that means that there exists another natural number m, so m in the set of natural numbers, such that, and we can use that other theorem that we have, that m minus 1 is less than or equal to nx is less than m. Right? So if that is the case, if I add 1 to everything here, then I have m is less than or equal to nx plus 1, and that's going to be less than m plus 1. So we have this particular little inequality here. Right? So that's pretty nice. Now notice that we have a couple things going on here. In particular, I have nx plus 1 is less than ny, and nx plus 1 is greater than m. Right? So if I sort of combine all of these inequalities together, what exactly will I have? Right? Keep in mind, if I subtract nx from both of these sides, we also have that nx is less than m. So we have that nx is less than m, and m is less than or equal to nx plus 1. And we also have that nx plus 1 is less than ny. Right? So that we have this compound inequality. And the only things that I really want to focus on are these two and that one there. In particular, nx is less than m, and that's less than ny. Right? So since n is a positive natural number, that means that n is not equal to 0. So I can divide both sides by this n. So I'm going to have x is less than m over n, and that's going to be less than y. So I have this particular thing here. Keep in mind that x and y were chosen to be non-negative real numbers, and m and n were chosen to be natural numbers. And since m and n are natural numbers and n cannot be 0, then we have that m and n is a rational number. Since x and y were arbitrarily chosen, that means we have that there always exists a rational number between any two chosen unequal real numbers. Right? So that means that Q is dense in R, and that implies that R is a separable metric space. So those are several different theorems and concepts associated to completeness and the separability of the set of real numbers. I hope you enjoyed this video, and I'll see you in the next video. Take care.